Could black holes be the key to a quantum theory of gravity, a deeper theory of how reality, of how space and time works? Well, I think so.
What are black holes hiding?
It's interesting. These objects, which have been known, I would say, for 40 or 50 years, but theoretically for the best part of a century, have always been fascinating. They're odd things. The simplest way to describe a black hole would be a region of space from which even light can't escape. Predictions that such objects existed go all the way back to the beginnings of relativity back at the turn of the 20th century. But actually, really, I would say into the 1960s, perhaps even into the 1980s, many physicists felt that because of the intellectual challenges that these predicted objects pose, many physicists felt that maybe nature would not create them. I even saw the great physicist Steven Weinberg say that he, in some sense, hopes that these things would not exist because they're so confusing. But we now know that they do exist, and so we have to face the challenges that they pose. Black holes are interesting because, going back to the work of Stephen Hawking in the 1970s, it turns out that they demand that we think about both quantum theory and general relativity together. And the quest to unify those two great pillars of 20th and 21st century physics into what's often referred to as a quantum theory of gravity is in some sense a holy grail for theoretical physicists. But the problem has always been, well, is there anywhere in nature that we can look to observe something that requires us to merge those two theories together? And black holes really are the unique place, as far as we can tell, in nature, where we can see a thing just sitting there in the sky that demands that we consider those two theories working together to hopefully reveal a deeper theory. The idea of black holes goes back a long way, actually, back into the 1780s and 1790s. There were two physicists, mathematicians, natural philosophers, whatever you want to call them, working at the time, that had the same idea, apparently independently of each other. One was a clergyman, an English clergyman called Mitchell, and the other was the great French mathematician Laplace. And they were both thinking in terms of an idea called escape velocity. So the escape velocity is the speed you have to travel to completely escape the gravitational pull of something, a planet or a star. For the Earth, for example, the escape velocity from the surface of the Earth is around 8 miles a second, 11 kilometers a second. If you go bigger, you make a bigger, more massive thing, let's go up to a star, for example, like the sun, then the escape velocity increases because the gravitational pull at the surface increases. And actually for the sun, it's somewhere in the region of 400 miles a second. It's really fast. What Mitchell and Laplace thought, and I think it's a very beautiful idea, is they imagined in their mind's eye, well, can you go bigger? Can you imagine more and more massive stars, giant stars, such that the gravitational pull is so large at the surface that the escape velocity exceeds the speed of light? And then you wouldn't be able to see them. There's a wonderful quote, actually, in Laplace's paper, where he says that the largest objects in the universe may go unseen by reason of their magnitude. And this is back in the 1780s or 1790s. So he's imagining stars where the gravitational pull is so vast that even light can't escape and you couldn't see it. Dark stars, I think he referred to them as. Now we know that such objects do not exist in the universe in that sense, in the sense that Mitchell and Laplace meant. But actually, they miss something, which is not surprising because it sounds almost paradoxical. But you can also increase the escape velocity at the surface of an object by squashing it. And it turns out that if you take the Earth and you squash it down and squash it down and squash it down until it's about that big, the radius just less than a centimetre, then the gravitational pull at the surface would be so great that light couldn't escape. And that is essentially the modern concept of a black hole. Now, Mitchell and Laplace's calculations or imaginings were based on Newtonian physics, so pre-Einstein. We come forward to 1915, Einstein published his general theory of relativity, which is a different model, a better theory of gravity. And it turns out that black holes also exist in general relativity. Now, if we come forward to 1915, Newton's theory of gravity is replaced by a better model, a better theory, which is Einstein's general theory of relativity. But the idea that there can be objects that can be compressed such that they trap light is also present in Einstein's theory. The first physicist to predict such a thing, or at least derive the mathematics that describes such a thing as a black hole, although he didn't know that they existed, was a man called Karl Schwarzschild. What Schwarzschild did was provide an exact solution to Einstein's equations that describes space and time, the distortion of space and time, in the region of a star, or at least an idealized star, which is a perfectly spherical, non-spinning ball of matter. It's a model, a simple model of a star. Now, Schwarzschild described or discovered the solutions to Einstein's equations that describes what happens to space-time outside such a thing way back, actually 1916, just after the theory was published. What Schwarzschild's solution also describes, though, although he didn't think in these terms at the time, was what that space looks like if you completely remove the star, but leave its imprint in the fabric of the universe behind. And that is essentially the theoretical description or the model of a modern relativistic black hole. Now, while Schwarzschild's solution, and by solution I mean we're to picture a distortion in space and time, a distortion in the fabric of the universe. While Schwarzschild's solution does indeed describe the simplest possible black hole that we can model in the universe, people didn't really think in those terms at all until later. You see in the 1930s, Einstein and a colleague of his, Rosen, for example, exploring that space-time and building models of what that space-time might look like. But I think it's true to say that really, certainly until the late 1930s, and actually arguably post-war until the 1960s, most physicists thought that such things would not exist in nature. So they were theoretically interesting, perhaps not practically interesting. The reason is that you have to create such a thing. So it's one thing to have a model of space and time that describes this object called a black hole, from which not even light can escape. But it's another thing for nature to actually make it. So if you go through the 1930s, there's a lot of papers. Actually, Robert Oppenheimer and a student of his, Snyder, wrote a very famous paper just before the war, which explored whether a real star in the universe, at the end of its life, could collapse and collapse without limit to form this geometry, this thing that we call a black hole. Just before the war, Oppenheimer and Snyder showed that under certain assumptions, a star could behave in such a way. But it wasn't really until the work of people like Roger Penrose and Stephen Hawking and several others in the 1960s that it really began to look as if nature would build these things. There's this great quote I remember with some fondness, actually. Arthur Eddington, a colleague of Einstein's, who was very English, very proper physicist. And he said, "Nature will prevent such absurdities from existing." Just, that's it. Nature will prevent it. Well, it turns out nature doesn't prevent it. We now know, and we've observed them, that stars do collapse to form black holes. And then theoretical physics moves on. So people accept that these things should exist, although it's true to say that we haven't actually imaged one until the 21st century. But in any case, people accepted these things should exist. More and more evidence mounted that they do exist at the centres of galaxies and at the sites of collapsed stars. But then we have to face the consequences. What does it mean for our understanding of the universe if there are these objects where space and time behave in a very strange way, where light is trapped, and where it would seem that anything that falls in is at the very least locked away from the universe forever. So to understand the conceptual problems that are faced if these things exist, then it might be worth just describing very briefly the Einsteinian description, the pure description in general relativity. A black hole, what do you see from the outside? Well, there's an event horizon surrounding the black hole. In some sense, it defines the boundary between the external universe and the interior of the black hole. The event horizon is very simply and a bit hand-wavingly, but it's a reasonable description. It's just, if you can imagine a sphere in space, and if you go across the boundary into the interior of this sphere, then even if you can travel as fast as the speed of light, you can't escape. So the event horizon separates the interior of the black hole from the external universe. We'll see a bit later why that's a bit of a hand-wavy description. But another description of the event horizon, which confused people all the way through the history of black hole research, actually, certainly to the early papers in the 1930s and perhaps even post-war, was the idea that the event horizon, when viewed from the outside, is a place in space where time stops. And that's a direct prediction of Einstein's theory of relativity from the external perspective. If you watched, for example, an astronaut falling in towards a black hole, then from your external perspective, you'd see their time pass more slowly, slower and slower and slower, as the astronaut approached the black hole, until on the horizon you would see their time stop. That suggested to many people in the early days that a star couldn't collapse to form a black hole. It confused them. They thought, well, if a star's collapsing, then does it not freeze forever in some sense on the horizon? So all sorts of initial early conceptual problems, which ultimately were solved. The thing about relativity, just the one sentence thing to understand, is that time can stop from one perspective, but time can pass at the usual rate from another perspective. And indeed, from the perspective of an astronaut falling into a black hole, then for a sufficiently large black hole, like the ones that we find at the centres of galaxies, the astronaut would notice nothing at all as they fell across the horizon into the interior of the black hole. So time passes at 1 second per second on the watch of an astronaut falling in, but from the external perspective, time freezes on the horizon. So black holes are full of these apparent conceptual challenges, which are actually not conceptual challenges at all. They're just a central part of Einstein's general theory of relativity. So that confusion was eventually dealt with and solved, and people understood, certainly by the 1960s, what these things are and how general relativity models them. There is a central problem, though, which is still not solved, which is, you put it this way, what lies at the centre, and I'll be careful with my language, what lies at the centre of a black hole. Now in pure, just in Einstein's general theory of relativity, actually it's not right to talk about the centre of a black hole, really. So what are we picturing? It's this thing called a singularity. You might think of it as an infinitely dense point to which this massive star collapses. It's kind of the natural way to think of it. But actually, just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that the singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time. So one way of picturing what's happened when a star collapses to form a black hole is that space and time are so distorted that, in a sense, their roles swap. And so what we thought of as an infinitely dense point, a place in space, at the centre of the collapse of the star, if you like, actually becomes a moment in time and the end of time, the singularity. But the nature of that thing was not and is still not understood. So that's a great mystery. And it's been long accepted that we will need a so-called quantum theory of gravity, a deeper theory of gravity, in order to explain the singularity. And for many, many years, actually, until quite recently, then people thought, well, there we are. We have a problem with the singularity. We don't really have any access to it. We don't have the conceptual tools to explore it. So it may remain a mystery for a century to come. It's not clear what to do. The great revolution in black hole research was to notice, and it began with Stephen Hawking's work in the mid-1970s, was to notice that actually there are conceptual problems at the event horizon of the black hole, not in this extreme place, not only in this extreme place, at the singularity, whatever that might be, but at the horizon. Now that was a real challenge and extremely interesting, because we strongly expect the laws of nature that we understand now, laws of nature that we have full mathematical and conceptual control of, to apply at the event horizon. And so that's why black holes have become so interesting. It's because we have a place where we think, we assume, and indeed we're right to assume, it seems, that we have full control of the physics. We understand what's happening, but there is a fundamental clash of principle between our two basic theories of nature, general relativity and quantum mechanics. And that is ultimately why the event horizon of a black hole and black holes themselves have become so fascinating and so important. The modern revolution in our thought, which is still ongoing, by the way, in understanding black holes and quantum gravity, really does begin with work that Stephen Hawking did in the mid-1970s. Stephen Hawking, in his own words, showed that black holes ain't so black. So we've described them as prisons, in a sense. We're picturing them as a region of space from which nothing can escape. What Stephen Hawking showed in a landmark couple of papers, a tour de force of calculation actually, is that if you consider quantum theory, quantum mechanics, in the vicinity of the horizon of a black hole, then you find that they glow, they produce particles, they have a temperature. This thing that we pictured in Einstein's theory as pure geometry, as just distorted space and time, actually emits particles. It's called Hawking radiation. And one way to picture that, and Stephen in his 1974 paper gives this, he says it's a hand-wavy description. So it's not a full description. You need the mathematics for that. But he gives this hand-wavy description, which is kind of a nice way to picture what's happening. The idea is to imagine, to zoom in on space in the vicinity of the event horizon of a black hole. If you zoom in on any piece of space, the piece of space in front of your nose right now, if you could zoom in and slow time down with a big microscope, you can picture what's happening as a series of particles coming in and out of existence all the time, so-called entangled particles. So it's a picture of what the vacuum of space looks like. Just to emphasize again, it's not a complete picture, it's not supposed to be precise, but it's a reasonable model of what's happening. So particles in and out of existence all the time. And that's happening everywhere, in space, everywhere that you look, in the most empty piece of space you could imagine. That's what's happening. In the vicinity of the horizon of a black hole, you can have the situation where one of those particles, those pairs of particles, is on the inside of the event horizon and one is on the outside. And then it can happen that the one on the outside, instead of merging back with its partner again, can escape into the universe. It's essentially made real by the presence of the black hole. So the other partner is interior to the black hole, and this particle heads off into the universe, removing energy from the black hole as it goes. And this rain of particles, this glow of particles, is called Hawking radiation. That has profound implications. So it's kind of a simple picture of what's happening. But the upshot is, imagine this thing. It's a black hole. It's glowing. It's just space-time geometry, but it's emitting particles, losing energy, therefore it's shrinking, which means that one day it will be gone. So black holes are not eternal prisons. They have a lifetime One day, whatever's in there is returned to the universe. The question was, the central question that was immediately raised by those calculations is this: what happened to all the stuff that fell in? The way I've described it, the way Einstein's theory describes it, is somehow that stuff goes to the singularity, whatever that thing is, the end of time, a region of space-time that's so convoluted and distorted that we don't understand how to describe it at all. But then, one day, the whole thing is gone. All that's left in the far, far future is Hawking radiation, those particles that were produced in the vicinity of the event horizon. The question is it possible, if you could collect all that radiation, all the Hawking radiation through the whole life of the black hole, is it somehow possible, in principle, that the information about everything that fell into the black hole throughout its history is imprinted in that radiation in the far future? Is that true, or is it not true? You might say, why did I ask that question? Seems like a bit of a random question. It's a very important question. Let's say that I take anything in here, in this room, a book, a table, the camera, right? Anything at all. And I set fire to it. I incinerate it. I destroy it in any way that I can. I could throw it into a furnace. I could put it in the heart of a nuclear bomb and explode it, right? Whatever, just completely incinerate it. In physics, in basic fundamental physics, then it turns out that if you could collect every piece of that thing that I detonated or incinerated, every quantum of radiation, every photon, every particle, everything, in principle, if I could just collect it all, and I was clever enough, then I could reconstruct the thing that I had destroyed. Information is conserved in the universe as far as we know. So every law of nature that we have says that information is conserved. The problem was that Stephen Hawking's initial calculation of the way those black holes evaporate away said that information is not conserved. Said that black holes are erasers of information. To put it very bluntly, the calculation said that once that black hole had gone, then even in principle, there is absolutely no way you could learn anything, reconstruct anything about the things that fell in, including the star that collapsed to form it. So information erasers, the only information erasers that we know of in nature. That was the initial picture of black holes as Stephen Hawking understood them back in the 1970s and 1980s. This became known as the black hole information paradox.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.